Okay, welcome back to the next session. I stopped at channel coding, right? So what I said in downlink transport channel processing, the transport block, okay, is added with the CRC bits. Okay, the purpose of adding CRC bits is to detect the errors, right? So that is the first step, adding CRC bits. Then after adding CRC bits, so we do the code block segmentation. So we do that based on the size of the transport block. Okay, that will be compared with the maximum codes block size. So which is equal to 6114 bits for turbo coding. Okay, if it is if the transport block plus CRC bit is greater than the maximum code block size, then code block segmentation is done. Okay, the new size of the code block segment will be equal to what I said. It is yeah. I think it is b divided by z minus l. If b is greater than z, and if b is less than or equal to z, then it will be 1 only. Okay. 6144 is the maximum code block size for the turbo encoder. Okay. And as I said, number of CRC bit sequence user is 24 bits. Okay. Yeah, this is what is shown here. The transport block with CRC is segmented further into small blocks, right? So, which is shown here, 1 to R. Then next step is the channel coding. Okay. So in channel coding, so different schemes and different coding rates are used for downlink transport channels. So which I said for transport channels, that is for downlink shared channel, paging channel, and multicast channel. For the turbo coding is used with a coding rate of 1/3. For broadcast channel, the coding scheme used is tail biting convolutional coding with a coding rate of 1/3. Okay, similarly, for downlink control information, so there are 3 different types of control information. One is downlink control information, DCI. For that, tail biting convolution coding is used, the coding rate of 1/3, and control format indicator. For that, block coding is used, the coding rate of 1/16, and for hybrid ARQ indicator, repetition coding is used with a coding rate of 1/3. Okay, so in channel coding, what happens? If I use a code rate of 1/3, means for 1 bit input, I get a 3 bit output, right? When I pass that 1 bit input sequence through the encoder. So to say here, one input row generates 3 rows of output, right? One input row generates the 3 rows of output. So that is what shown here. See here in the top I wrote R rows. So this I got with the code block segmentation, right? And each row after channel encoding will be converted into 3 rows. Row 1, row 2, row 3. So like for 1 power 0, 1 power 1, 1 power 2. Okay. So one row is converted into 3 rows. That is the effect of channel encoding. Okay, channel coding. So as I said here, in case of LTE, see convolutional encoder with code rate of 1/3 is used with a constant length of 7. So here the trellis termination is very important, okay, because the transmitted code blocks will be of finite length. Okay, so we need to perform trellis termination at the end of each code block. Okay, why we need to do the trellis termination at the end of each code block? It is required to restore the state of the encoder to the initial state for the next code block. Yes, we need to reset. That is what the purpose. Okay, so to do that, there are two methods. Okay, to what I said to for trellis termination. Okay, to perform trellis termination at the end of each code block to restore the state of the encoder to the initial state. Okay, for the next code block, there are two ways. Uh, Before saying what are those two ways, just I'm showing the diagram of tail biting convolutional encoder. I don't know whether is it visible or not. The diagram is so small. Okay, anyway, I will tell you here there are six uh, flip-flops are there. So delay elements. So I have written that as S0, S1, S2, S3, S4, S5. So totally six delay elements. And for the first flip-flop, the input sequence is applied, that is CK. Okay, and then with that combination, output of each of the delay element or XOR or modulo 2 operation is done, and finally I am getting the three coded sequence. Okay, means for 1 bit input sequence, I am getting 3 output sequence, that is with 1/3 encoder. Okay, that is what the diagram is. So as I said, for release termination, there are two ways. One is padding, another one is tail biting. So in case of padding, what happens is the zeros are padded at the end of the code block. Okay, by padding zeros at the end of code block makes the encoder to turn into the state 0. Okay, at the end of the code block. So that is the starting state for the next code block. I repeat once again, there are two methods to do the trellis termination. One is padding and another one is tail biting. Okay, one is padding, second one I said tail biting. In case of padding, what is done is the zeros are padded at the end of the code block. Okay, so by padding zeros, okay, makes the encoder to turn it to the state 0 at the end of the code block. So that is the starting state for the next code block. Okay. So the problem with this method is here, because we are adding additional zeros. Okay. That leads to wastage of bandwidth. Sorry. Okay. So additional bandwidth is wasted due to the extra zeros that are added at the end of each code block. Okay. So for the example, what we have considered, I have considered 6 flip-flops, right? So I need to add 6 zeros. So that is the drawback of this method. So the most efficient method is the tail biting. Okay. So tail biting is the most efficient method of trellis termination. So what is done in this tail biting method is the information bits from the end of each code block are appended to the beginning of the code block. So it is almost like a cyclic prefix. What if you have remembered in case of OFDM, so we do tail bits are appended at the beginning. That is to avoid intersymbol interference between the adjacent OFDM symbols. The same concept is applied here. Okay. So information bits from the end of each code block are appended to the beginning of the code block. So by doing so, okay, by doing so means appending the tail bits at the beginning of the code block, and when these appended bits are passed through the encoder, it ensures that the start and end states of the encoder will be same. Okay. So for example, means for the example what I have considered, if the input bit sequence is say C0, C1 and so on up to CK minus 1, the initial value of the shift register should be set to, so there are 6 flip-flops I said, right? So S0, S1, S2, S3, S4, S5, okay, are the 6 flip-flops. The initial states of those shift registers should be equal to tail bits, that is from CK-1, CK-2, CK-3, CK-4, CK-5, and CK-6. Then I can say the initial state and the final states of the shift register will be same. So that makes the trellis termination. Okay, so here the parity bits that are generated from the appended bits in the beginning of the code block are discarded and not used for the transmission. So any doubts you have in this so far? Hello? Do you have any doubts? Is it clear whatever I said?
Sir.
Yeah, I said there are two ways to do the trellis termination. One is padding, another is tail biting. In padding, what is done? In padding, zeros are padded at the end of zeros are padded at the end of each code block, I said. So that leads to wastage of bandwidth. That is the drawback, right? So in case of decoupling, what happens? Tail bytes are appended at the beginning of each. So this leads to the initial state, which is equal to final state. Okay. Okay, that is what is done. So this is the diagram of turbo encoder. Okay. So turbo encoder is also. So I'm not going about this. Already I said what it is. Okay, let me go to the next one. Yeah. So see the problem. I said that tail biting is one of the most efficient trellis termination, right? Because here all the bits are afforded with the same amount of error protection, and there is no code rate loss, okay, compared with the zero padding technique. But here the decoding algorithm will be more complicated. So that is the challenge in case of tail biting. Okay, so this is all about channel coding. So next, after channel coding, what will be this one next step? That is rate matching, right? So why rate matching is required? So this rate matching in LTE performs interleaving as well as repetition, okay, or we say puncturing, in order to generate a transport block that fits the payload size determined by the modulation scheme and the number of resource blocks allocated for the transport block. Okay, so that is what the rate matching is. So it will generate the transport block. Okay, to generate transport block that which will fit the payload size. That payload size is determined by the modulation scheme and the number of resource blocks allocated for the transport block. Okay, for that rate matching is required. That is performed by using interleaving and repetition coding. Okay, so this rate matching is defined per coded block. Okay, rate matching is defined per coded block and consists of 3 stages. One is the interleaving, second one is bit collection, and third one is bit selection. Okay, these are the 3 different stages involved in rate matching. So I hope you understand this diagram. So in case of channel coding, what is done with the 1/3 coding rate? One input bit stream, okay, is converted into 3 output bit stream. Okay, here with the rate matching, okay, with the rate matching, here we are converting those 3 rows, okay, 3 rows into a single row, the reverse process. Okay, so here what I've shown 1 power 0, 1 power 1, 1 power 2, that is 3 rows will be converted into a single row, that E10, E11, and so on. Okay, so in case of rate matching, right, so each set of 3 rows of input stream becomes 1 row of bit stream. Okay, so how do we do that? We do that by using those 3 steps, by interleaving, okay, by bit selection and bit collection. Okay, here the question is how to convert that set of 3 row into 1 row. Right? Is it just by concatenating the 3 row into 1 row, or is it just random mix of the 3 row, or is it by interleaving the 3 row? So last is the solution, interleaving, right? Then selection and collection also, bit selection, bit collection. So I hope that is clear. So interleaving, how do we do the interleaving? So interleaving is performed to spread out the occurrence of bursty errors, okay, across the code block. Okay, to spread, like, okay, to spread out the occurrence bursty errors across the code block, the interleaving is done. So that will improve the overall performance of the decoder. And this interleaving is performed separately for systematic and as well as parity bits. Okay, that is about interleaving. And the bit collection stage is required to place the systematic and parity bits in the right order as needed by the decoder. Okay, so to place the systematic and parity bits in right order, the bit collection is required, and bit selection is needed in order to repeat, okay, some of the parity bits to create the required payload. So for that, bit selection is required. Okay, so I hope is it clear? 3 steps in rate matching. One is interleaving, bit collection, and then bit selection. So how do we do the interleaving? So we do interleaving to spread the bursty errors across the code block. So that will improve the performance of the decoder. And it is done separately for systematic and parity bits. Okay, bit collection stage, I said it is required to place the systematic and parity bits in right order as required by the decoder. And bit selection stage is required to repeat the parity bits to create the required payload. While doing, see, this is sub-block interleaving we do. In case of interleaving, we do the sub-block interleaving. So here the interleaving is performed independently for each bit stream, okay, done by the block interleaver with the inter-column permutations. I will show the diagram, then you will understand how it is done. Okay. Then about bit collection. So here a virtual circular buffer is formed, okay, by collecting bits from the interleaved streams. Fine. So here then the systematic bits are placed at the beginning, followed by bit interlacing of the 2 interleaved parity streams. This interlacing will guarantee the equal number of parity 1 and parity 2 bits are transmitted. If I show the diagram, you will understand. This is what the diagram is. Okay, so here systematic stream, okay, then parity stream 1, then parity stream 2. Okay, that is we get from the coded block. So then sub-block interleaving is done. Okay, sub-block interleaver from systematic stream and as well as from the parity stream, we do that. From that, so bit collection is done. So in bit collection, see proper arrangement of the sub-block interleaver is done here, right? So one from here means some bits from adjacent will be added here. See, from this block it connected here, From this block, it is connected here. Right? Then the bit selection. Bit selection is concatenation of those blocks. Okay. So this is just elaborated explanation compared to the previous one. So what I'm showing here is I'm showing 3 sub-block interleavers. Okay, because I'm getting output from the rate matching 3 this one, right? So each is applied, each sequence is applied to each sub-block interleaver. Okay, so the 3 lines of turbo coding output gets into this rate matching block and comes out as a single line. So here with the bit collection and bit selection will come out as a single line, EK. So there I have shown from 3 rows into a single row. Okay, that 3 rows into single row is done with these 3 processes. One is sub-block interleaver, bit collection, and bit selection. So all these 3 steps leads to one row of block. Okay, right? Means it will come as a single line of bit stream. So I think about that I said. So just some more explanation to say about bit selection. So here we select the output bit sequence. The sequence length, as I've taken here example L, should first be determined. Okay, we need to determine the sequence length. So that sequence length depends on the number of allocated resource blocks, then the modulation scheme and the MIMO mode, whether it is SISO or MISO, like MIMO. Okay. So in case of bit selection, we need to select the output bit sequence. Okay, the sequence length is L. Somebody is doing something. Okay, fine. So what I said, I was telling here, right? So we need to select the or the indicator. Okay, so to select the output bit sequence, no. Okay, let me see it. Here to select the to select the output bit sequence. Okay, output sequence, the sequence length. The sequence length L has to be determined. Okay, that depends on what I said. That depends on the number of allocated resource blocks, modulation scheme, and the MIMO mode. Okay. 6. Okay, then L bits are read from the virtual circular buffer, I said. So the starting point of the bit selection depends on redundancy version of the current transmission, and which is different for different retransmissions associated with the hybrid ARQ process. Okay. So from one hybrid ARQ retransmission to the next, even though the number of bits are same, the parity bits that are repeated will be different. The parity bits that are punctured or repeated can be different. Right? So this is what done in bit selection. Okay. So I think with this my lecture is over. So from your side, you can ask any doubts if you have. You can chat me also. If you have any So no doubts? So everything understood then. Service work implementation. Yeah. So then no doubts. Okay. Just I will run once through. So this is the overall this and this is the overall uh, downlink transport channel processing. I think I completed channel coding processing. Okay, channel code processing I completed. So now let me take about this modulation processing. Okay. So modulation means after code block concatenation, it will be means this is a right code block concatenation. After 1, 2, 3, 4, 5 steps, it will be applied to the scrambler. So here the scrambling of the coded bits in each of the code words to be transmitted on the physical channel. Okay. So let us see what are the different types of scrambling techniques which are used in LTE and all. Then output of those will be applied to the modulation mapper. So modulation of scrambled bits to generate the complex valued modulation symbols is done at this stage. Then the mapping of the complex valued modulation symbols onto one or several transmission layers is done in layer mapper. Okay, so output of that is given to the precoder. In pre-coding, okay, the pre-coding of the complex valued modulation symbol on each layer for transmission on the antenna ports is done. Okay, then output of the pre-coding is applied to the resource element mapper. So this mapping of the complex value modulation symbols for each antenna port to the resource element is done at this stage. Then output of that is given to the OFDM signal generation. So here the generation of complex value time domain OFDM signal for each antenna port is generated. Okay? And it will be transmitted over the air. So this is a little bit complex compared to the previous one. So let me take up this in the next session. Okay. So to understand these things properly, you should have proper understanding of that OFDM modulation, these things. Okay. Okay. Then just to recap, just I will go through what I said. Channel coding is the combination of error detection, error correction, read matching, interleaving, so on. And it provides error control mechanism for data transmission using forward error correction code and error detection based on the CRC code. Okay. For shared channels, error control mechanism is coupled with the retransmission mechanism. Okay. And this combined use of error control mechanism and retransmission mechanism improves the link reliability in the fading channels. And as I said, CRC is used to provide error detection on the transport block, and these CRC bits are generates the parity bits by cyclic generator polynomial. Okay, and the number of parity bits can take value of 8, 16, or 24. And here 24-bit CRC is the baseline for downlink shared channels. So this is what I said here. Transport block from MAC. Okay. The goal is to convert the transport block from MAC into a series of bit stream data to be transmitted. That is the goal. So that is what to do that. These are the different steps involved. Okay. That is, we attach CRC, then we do the code block segmentation, then we do channel coding, then rate matching, then code block concatenation. So in channel coding, I said there are two types of channel coding we use. One is tail-weight convolutional encoder with a code rate of 1/3, which is used for broadcast channel. And another is turbo coding, which is used for downlink shared channel, a multicast channel, and a paging channel with a code rate of 1/3. Okay, and even for control information also with a different coding schemes and different coding rates is used for DCI, that is for downlink control information. Turbo codes are used. Okay. So here, just to show how CRC is added to the transport block, right? And I said how code block segmentation is done. So based on what? The maximum code block size is 6144. Okay, 6144. And the transport block with CRC will be compared with this maximum code block size, and accordingly the decision will be taken to have a smaller code block. Okay. And this is what the thing. So single transport block is split into multiple small blocks, is done in code block segmentation. Then in channel coding, as I said, that single input bit stream is converted into 3-bit output stream with a coding rate of 1/3, right? And in case of Okay, here I told about how means what are the different methods to do the trellis termination. One is padding, another is tail biting. In case of padding, zeros are padded at the end of code block to make the state of the flip-flop to 0 at the end of each code block. That is necessary for the next code block. The problem is with this method is it wastes the bandwidth because it adds so many additional zeros, right? And tail biting, I said, is one of the most efficient method. Here what is done is the information bits from the end of each code block are appended at the beginning of the code block. So by doing so, the appended bits are passed to the encoder and it ensures that the start and end states of the encoder are same. So with this, what happens? For all the input bits, the same amount of error protection, and there will be no code rate loss. Okay, but the decoding algorithm will be more complex. This is what the drawback of this bit encoder. And as I said, the rate matching is done by using interleaving and as well as replication. So this is necessary for generating the transport block that fits the payload size determined by the modulation scheme and the number of resource blocks allocated to the transport block. So this rate matching is done for coded block and it consists of 3 steps. One is interleaving, bit collection, and then bit selection. So in channel coding, single bit stream is converted into 3 output bit stream. In case of rate matching, that 3 bit stream is converted back to a single output bit stream. So that is done by using interleaving and bit collection and bit selection. So this is what is done here. I think I told about that, how sub-blocking, interleaving, and bit selection and collection is done. I said so bit collection, why bit collection is required to place the systematic and parity bits in the right order. So bit selection is required to repeat the parity bits to create the required payload. I think this is very important, what I feel. This bit selection is needed to repeat parity bits to create the required payload. And this bit collection is required to place the systematic and parity bits in the right order as needed by the decoder.